this time. So I will introduce Prof's business.
Okay. I'm here to introduce Anastasia Yilmaz in our seminar session. Anastasia is a last year PhD student at the Astronomical Institute of SEC Academy of Sciences, Prague, and Charles University. And she works under the supervision of Iris Vodova and Victoria Greenberg. And the main focus of her PhD thesis is the evolution of accretion disk around black hole in X-ray binaries, of course, and across the luminosity scale. So I give the floor to Anastasia.
Thank you. Thank you for the introduction. I also would like to mention some of my colleagues that really greatly helped me get through my PhD and also contributed a lot to the work that is now being included in my thesis. And just to give you, or anyone who is not really familiar with the topic, what by X-ray binary I will mean is usually systems that either harbor neutron stars or black holes, and the main powering mechanism behind it is accretion onto the contact object. And there will be two different mechanisms actually dominating the way of accretion happens, and it will be dependent on the mass of the component or the donor star. So in case of highly massive donor star, you will have stellar winds actually dominating the accretion flow. You will still be able to have accretion flow happening through Roshlov overflow, which is the dominant ignition for low mass X-ray binaries. But in that case, you will not be able to have significant stellar winds to actually contribute a lot to the formation of the accretion disk. The reason that we call them X-ray binaries is because they are mainly visible in X-rays, but due to the structures of the accretion disk and also the mass accretion rate, they will be able to emit multi-wavelength radiation, especially in UV, infrared, and in case of the presence of relativistic jets, you will be also able to see them in radio. And I will briefly introduce the ultraluminous X-ray sources, which I also include in the concept of X-ray binaries. But there are some people that I really know to actually want to have that distinctly separated. The reason that I actually included in this presentation is because I'm trying to kind of bind the two ends of the luminosity scale, in which I'm trying to build a connection between the known black hole X-ray binaries and also some of the ultraluminous X-ray sources. So ultraluminous X-ray sources are off-center point-like sources where you will be able to see the X-ray luminosity reaching 10 to the 40 or 41 arcs per second. They were actually in the early 90s were thought to actually harbor the best environment to have an intermediate mass black hole. But in 2014, if I'm not mistaken, we were able to see pulsations coming from them. So now there's a growing population of detected neutron stars, and also it is now believed that the super Eddington luminosities reaching these actually can be powered by neutron stars. Although it still does not eliminate the possibility of them having actually intermediate mass black holes, but the identification of that at such high distances is very difficult through dynamical mass measurements. As you can see on the left side, I mean at least for the people present in the room, that you can see the spectral shapes are very different from one another. And you cannot really see a clear evolution in the spectral shapes as you go with the luminosity scale, which is basically the y-axis. So it's not really that easy to make a connection between even one source to another, but it's a very nice, interesting population of sources that I want to study in the future. Unfortunately, they do not show clear signs of evolution like we see in the black hole X-ray binaries. I will talk about them in a very short while. So it's a little bit difficult to actually understand if there's an evolution of an accretion disk or an accretion flow with regards to increasing luminosities or not. So I see this as a very nice population that we can use to test different accretion theories that are currently available. So if we want to look into the components of the black hole X-ray binaries, it's much easier to actually talk about it in contrast to X-ray sources. For simplicity, we will have main X-ray emission coming from the innermost regions of the accretion disk. You will also have a corona, which basically upscatters the seed photons coming from the accretion disk to much higher energies, which you will be able to see from this emission, while the accretion disk emission will only be dominating very low energies, and it will contribute to much less emission to the overall spectrum if your specific source is in a specific accretion state. You will also be able to have reflection happening. What happens is that your seed photon will actually get inverse Compton scattered in the corona, and then it will actually sometimes be able to come back on the surface of the accretion disk, from which, when it reflects, it will show signs of iron K alpha line emission, which you will be able to see around somewhere between 6 and 7 keV. In the case of a launching of the accretion disk wind, which is strong outflows coming from the surface of the accretion disk, you will also be able to see, instead of an emission, you will be able to see some absorption, which will be again around the same energy level, but it will not be able to. You will not be able to actually show it in one spectrum, because the accretion disk wind launching mechanisms usually associated with much higher luminosities, while we are usually seeing the reflection component at much lower luminosities. And in the case of the reflection component, it will depend strongly on the position where it's emitted from. So if this reflection is coming from the innermost regions of the accretion disk, due to the relativistic effects, it will be broadened. But if this component is going to be coming from much larger radii, this will be much narrower, and you will see the difference between the components when you plot them together. And you will, as I also mentioned, that there might be in some cases relativistic jets launching in the lower luminosity scales, but this is mainly dominantly observed in radio bands. So the black hole X-ray binary population is actually very interesting, because they do seem to follow a very nicely defined shape when you look at the relationship between the X-ray hardness, which tells you how, if you look at the spectrum, it will tell you how much of the relative dominance between the soft component, which is the lower energies, is going to be changing with the harder component at higher energies. That specific evolution will tell you whether your corona is dominating your spectrum or your accretion disk is dominating your spectrum. So that will also be able to show you which accretion state you are in. So when you look at the hardness intensity diagram, for specifically this was derived by RXT observations for about 25 of these sources. So you will see that they do not only follow it once, they follow it constantly, unless there's some specific things happening characteristic to the outburst that we're talking about. They will do this loop constantly, and they will do it across all of the sources. There are now new ones that are found to actually not follow the specific path, but it's not really that clear whether or not there's something else happening. So as I said, using this Q track, we are able to track where the accretion disk can be located at, or you can also track if there might be jet emission, or you can track how much of the coronal emission is dominating. Both of these states will be relevant for different reasons. in my case, I want to look at how the accretion disk is evolving. You can use reflection components to measure your black hole spin. You can use the low Hart state in this case if you want to look at how the coronal structure is, the geometry is. So each state will correspond to different purposes, and each state will be still as important as the case in mine. So many of these sources are usually in a quiescent state. There are some persistent sources, but in a more general case, once the accretion is ignited, the source will rise on the intensity scale, but it will be more or less in the same hardness ratio. So which means that there's some luminosity increase, where we usually see it as an increase in the mass accretion rate, and your accretion disk is getting forward, like closer and closer to the black hole. And in this case, you will have your corona much more extended, and you will have a very strong radio jet. And as you go towards the intermediate state, which is also characterized by a hard and soft intermediate state, but I will not really go too much into that, you will see how your jet actually being quenched, which means it's moving further than the black hole, and your accretion disk is actually getting closer and closer to the black hole, while the corona might actually be staying, or it might be actually shrinking in the size. And you will also see this change in the hardness ratio, where you will have your accretion disk emission actually having more and more powerful emissions in your X-ray spectrum. And when you go to the high soft state, which means the coronal emission is either present but very low, or really not present at all. It also depends on the sensitivities of your instrument, of course, but in a more general sense, we assume that the contribution is not that significant. And your accretion disk is actually closest to the black hole, depending on what accretion disk geometry you want to adopt. There are maybe two possibilities that we can consider. It is either extending all down to the innermost stable circular orbit, which will define the limit up until which you can have circular stable orbits. So if you cross that significant limit, you will no longer be able to sustain a disk formation, and your material will plunge onto the black hole in more or less spiral shape. Or in some models, you can actually assume that your accretion disk is going all the way to the event horizon, but that requires a different accretion disk solution. And once you reach that state, and your mass accretion rate is starting to get lower, the orbital periods can actually change that, and your source seems to evolve following this lower part all the way to the end of the low Hart state. So I keep talking about the accretion disk solutions. Now I will tell you what they are exactly. So in a more general sense, people usually like using a very simplistic, non-relativistic Shakura-Sunyaev disk, where you assume a geometrically thin. Sometimes it's a very thin slab. Sometimes they don't even consider any thickness to it. It's a geometrically thin, but optically thick accretion disk solution. For anyone familiar with an X-spec environment, this is a model called this PB. And in a few months after its publication, Novikov and Thorne actually decided, okay, let's have some general relativistic solutions of the specific Shakura-Sunyaev disk, which includes all of the calculations of the photon paths around a black hole. In the Shakura-Sunyaev disk, it's a pure multicolor black body emission. So you basically have a specific black body emission at specific radii with a specific temperature. So what you end up seeing in your spectrum is some of them. But in the case of a Novikov-Thorne disk, it's a little bit different than that. And as you go, as you increase in your luminosity, the accretion disk geometry is expected to change. So the more you increase your luminosity, the thickness of your disk is expected to change. It's not that clear whether it actually changes as a whole or there are some deviation points where you have still your Shakura-Sunyaev approximation, and then the rest is changing. So it's not that clear, but it's assumed that's no longer thin, but it's a slim disk approximation. And once you actually transition to that, the radiative cooling mechanism, which basically cools down your disk and actually makes visible to you in X-rays, is now accompanied by an advective cooling mechanism where your heated disk will remove the heat from that specific region of the disk by radial advection. And if you actually want to go look down all the way to the lower end of the luminosity scale, this will more or less be called the advection-dominated accretion flow. But it's also not that well understood because, one, in that specific case, the radiative efficiency of the disk is strongly affected by that added advective cooling mechanism. So it's also less luminous. So, but it's not that easy to actually provide a very nice solution to it. So the accretion flow is also not that well understood in terms of the geometry. There are also other solutions called puffy disks, which is actually a very nice stationary solution to higher luminosity scales, and that's a very nice theory that we can actually start including in the study of ultra-luminous X-ray sources, because it also includes the effects of beaming. There's also another model called JetSat, and which basically tells you that gives you a bit of an accretion disk solution where in the innermost part of the accretion disk it's a jet emitting disk where you actually see the radio emission, and then the outside is assumed to be a Shakura-Sunyaev disk. And I will talk about the MAD in a bit. So the global studies of these accretion disks in many of these black hole X-ray binaries actually showed that there are some very nice deviations. When you look at, I call it nice because it's very interesting in my case, and it gave me my project for my PhD, is that when you look at the disk luminosity, which is on the y-axis, versus the disk temperature on the x-axis, it is actually a little bit different than the exact relationship you would like to see. When you look at the higher luminosity scale regions and lower luminosity regions, there seems to be a little bit of deviation. And when you also look at the evolution of the innermost edge of the accretion disk, yeah, me neither. When you look at the innermost edge of the accretion disk and where it's located with respect to the disk temperature, there seems to be a little bit of difference. So when the expectation is that when you get closer and closer to the black hole, your disk is expected to heat up even further. But on some level, it's either stable or it is something different happening. So I will quickly talk about what I did for the spectral analysis specific to the black hole, three black hole X-ray binary cases I will talk about. I attempted two types of fit with three accretion disk models. I chose specifically those states in which the contribution by the reflection component is not that significant, or I can model it properly with a relativistic reflection model. So the first one is the non-relativistic disk solution, disk PB. For the Comptonization component, I used a simple power law, but for anyone wondering, I also tried a few other models to see if they actually change any of the results, and things seem to be very consistent. I used about almost 2,000 RxTE observations to be able to do this analysis. And for the relativistic disk models, some of you have seen the KRBB, and I think some of you also have seen the KYMBB. So both of them actually assume a Novikov-Thorne accretion disk, but KYMBB has a little bit more freedom into the choice of parameters that you have. The main, and I think to me the most important change in between the two models is that KRBB is assuming that your inner edge of the accretion disk is located at exactly the innermost stable circular orbit, because it's actually a model that wants to get a measurement of the black hole spin. But with KYMBB, you can have it as a free parameter and can see the evolution of this inner edge with respect to the accretion state you are in. And the other parameters like the black hole spin, black hole mass, inclination angle, and distance to the source is very much the same. KYMBB also has some other calculations. You can either calculate, for example, a specific region of the accretion disk, or you can extend it to the whole slab. It's a very nice model, but a bit pain in the butt to work with. So we've seen this, but we will have 3 different evolutions. This is very interesting to see because there seems to be some sort of a distinction between the paths that the sources follow in that temperature versus luminosity relationship, even though they seem to follow the same Q-shaped path. So there will be some short deviations when you look at the exact points on the Q path, but it's more or less the same. So it's a very interesting outcome of it. But there are a few things that actually make it more interesting, in a sense that some actually argued that when you follow this line, increasing your luminosity, and then you have this turnover, because it also kind of corresponds to a specific portion in the long-term light curve, there might be some sort of a change in the accretion disk structure. As I said, the radiative efficiency is very much dependent on that accretion disk solution that you choose. So there might be some sort of a change in the accretion structure with increasing or decreasing luminosities or mass accretion rates, and then you might be able to see that kind of a relationship. But there's one problem with that specific idea, is that when you look at GX39-4, for example, this is reaching about like a little bit above 10% of the Eddington luminosity, while LMCX3 reaches very high, like even 40 or 50% of the Eddington luminosity. So there seems to be some sort of a discrepancy with that idea, because if actually that was the case, that you are having an accretion disk solution problems in your modeling, then this would not be happening with LMCX3. Because also with the case of GROJ1655-40, which is another very nice example of this evolution, you are not even reaching 10%. And when you look at some other sources which are very high in the luminosity, this is a ULX in M81X1, you see that, okay, this plot is a little bit inverted, but you see a similar relationship as you see in GX39-4, for example. So in this case, there is some sort of a, like a subpopulation where you only have the increasing branch that you expect to see, but you have in some cases you have that deviation branch, but without the exact increasing branch, and in some cases you have a combination. So to me, it seems like, yes, there is some sort of a distinction between all of these systems, but it seems also like there is also a nice connection that we need to find in the future. So as a kind of a summary, as I said, most of them are just commonly evolving through a similar path, but they do not seem to show similar patterns in their observed luminosity and temperature. But we also looked at how the launching of other mechanisms, other components, especially the accretion disk wind and also the reflection component, might change. It seems like the launching of the accretion disk is actually not happening in the states where you have these deviations. And in the case for GX39-4, we were able to test whether or not that reflection component was contributed to that temperature change we saw, which was also not the case. So I'm left a little bit with more question marks that I need to look at. And I also integrated a few other instruments to look at what is happening at those two ends. I tried using another instrument, Integral, to see if the better modeling of that Comptonized component might change what you are seeing. In that case, yes, the photon indices were able to, get into a better constrained value, but unfortunately that did not really change the temperatures that significantly. I also tested whether they can actually change the measurement of the black hole spin, which in that case was very statistically significant within the nice confidence levels. And the most important part, on the other hand, happened with this lower end in GX39-4, in which I was able to find some simultaneous XMM Newton observations, and then I combined both of them, and these temperature values were able to recover to the lower end of this distribution here. So also the other part that I want to mention is when you start including the relativistic corrections to your observed spectrum, but you also account for an inner disk radius where it's not actually at your ISCO value, you are able to see a very important result, where if you look at the upper plot, this is with the non-relativistic disk model, and when you look at the lower part, these observations were able to get recovered to what you see. There's a little bit more scatter introduced to the relationship, but that's more of a statistical issue rather than anything else. And more importantly, when you look at the evolution of the inner edge of the accretion disk and what values they lie at, with a non-relativistic disk models, that gives you a very unphysical value. For example, in some of the cases, I will quickly show it from here. If you look at these specific observations, this actually, they seem to go below 1 RG. And this is, I think, 7 solar masses black hole, and it seems like a very unreasonable result. There were some people actually use this to talk about whether it can be a maximally spinning black hole, especially for GRO J655-40, but it seems like a very unreasonable way to do things. And when you look at how these parameters are changing with KYMBB, you are actually able to see much more reasonable results. And when you look at how they are comparing with different ISCO values for 3 different black hole spins, they actually seem to align much better. So I want to now change the narrative a little bit in a different direction. So remember these 2 specific plots. Now there's a very nice outcome of, or maybe not like an outcome, but more of a 2-way relationship between the black hole spin and the evolution of accretion disks. If you look at the distribution of the measured black hole spin with respect to the disk luminosity, you will end up with 2 different distinctive distributions. For LMCX3, there seems to be a very nice, if you exclude some of the plots, very nice confined space, while the accretion disk luminosity is actually seems to be affecting the measured black hole spin for GRO J1655-40. Yes, the choice of the model actually depends a lot on the modeling of the accretion disk emission, but there seems to be a very distinct evolution between the 2 parameters when you look at the whole sample. So this is not only specific to LMCX3 and GRO J1655. It also is present in GX39-4, and there even something is more different happening in LMCX1. We were able to then see, actually confirm the lower spin measurements of LMCX3 with the XP observations, and it was a very nice confirmation of what we were trying to say. One of the things that were actually introduced to explain that evolution that I basically mentioned multiple times now is that there might be some changes in the spectral hardening factor. The spectral hardening factor means that so with increasing mass accretion rate, your accretion disk is expected to heat up. And once it reaches a limit temperature, which is around, like according to the Sokuras-Tuniev solution, it's around 1.1 kV, then your accretion disk atmosphere is supposed to be much denser, and the upscattering of your accretion disk emissions from the surface is going to be much more dominant. Which means if you want to track the energy evolution of the emitted photon from the accretion disk surface as it goes through the atmosphere, it will actually increase in the temperature and in the energy. So what will happen is that your accretion disk emission that was only dominated in a very, very short, in a tiny space in low energies, will actually shift it towards higher energies. So there's a way that people actually introduced very early in the study that you can kind of assume a ratio between the two, which is usually assumed at 1.7. This is called the color correction factor, FCOL. And unless you have very nice self-consistent modeling of the accretion disk atmosphere, this is very hard to constrain. But this is actually a free parameter you can use in KBB and KYMBB. And when you look at the evolution of this parameter with the evolution of accretion states, there's a very nice correlation, and it's very consistent with the theoretical models. But it's unfortunately not that easy to have a good estimate. People said that the disk will not change in the position. So it will always terminate at ISCO, but the temperature and also the contribution from that accretion disk atmosphere is going to be the one driving the changes in the temperature that you will see. I personally do not like this argument, but it was one of the things that I needed to try before I can make any kind of claims. Unfortunately, the recovery in these temperatures that I showed you with KYMBB was not really present in the case of letting the color correction factor change within the analysis. And we were not really able to see much of an improvement, probably because of the strong degeneracies between the black hole spin and also the color correction factor, both of which will affect your accretion disk temperature in a very similar sense. So now I want to talk about a new ultraluminous X-ray, a transient one that I am now going to be, probably it will be published in a very short amount of time, which is in M51. M51 is one of the most ULX populated galaxies in the close-by universe. I think up to date there are almost 10 ULXs present and reported in a specific galaxy, and now this is a new one, but it's a very different in a sense that it's a little bit difficult to fit it into one category. So this specific one that we see only going through an outburst only once in almost 2 decades of observing time, we were able to track with XMM Newton, Swift, and Chandra. This specific outburst lasted about 80 days, although there's a little bit of room of error because we were not really able to see any further observations with Chandra. So it might actually be continuing a little bit further, but more or less it's about 80 days. And we do not actually see any of the multi-wavelength components, neither in simultaneous Swift ULOT and XMM Newton OM observations. We were able to use some HST observations before and after the outburst, but we were not able to see significant changes that might point towards any signs of the outburst. And we actually have a very soft spectrum with a photon index with around 2.7. So the interesting thing about this specific case is that the outburst cannot really be identified as the beginning of a typical black hole X-ray binary outburst, and it's also not in a sense that the outburst is not typically present in other transient ULXs. And we were not really able to see any pulse emission with a pulse fraction upper limit below 30%, which is actually consistent with when you combine it with the soft spectrum, it's consistent with an accretion disk emission. In the case, if you are able to actually see this pulse emission from a ULX, This is usually thought to be originated from the inner accretion flow, where you will be able to see much harder spectrum rather than 2.7 photon index. So just a quick disclaimer. This is not going to be in the paper, but I also realized that this actually shows it above 10 to the 39. These points are actually in a little bit below, so there's a mistake, but I need to still show this specific plot. So we wanted to then try and see what we can do in comparison with known TDEs. So this is actually a very nice sample we can compare. Even if you can assume many of these sources are found within a redshift of 0.5. So they are usually expected to be observed in a very local universe. So even if you assume an error bar on the distance of the source up to 0.5 or 0.6 redshift, the luminosities are much, much lower than the observed X-ray and optical UV TDs. And when you also look at if you can get a constraint on the disk temperature from adding additional disk BB component to the analysis, then one of the observations actually seem to show a much hotter accretion disk. So in this case, in the case of a TDE, the accretion disk can actually form, but since they usually are expected to happen around either intermediate or supermassive black holes, the disk temperature actually is supposed to be much lower. So there's an inverse relationship between the two. From that discussion, we can also infer whether it's actually an intermediate or supermassive black hole, or we are dealing with a stellar mass source. In the case, if we actually take this specific temperature and with no other multi-wavelength components, especially in UV and even in optical, we have to stay within a stellar mass accretor, but it's also not that easy to get whether it's a neutron star or a black hole because we do not see any pulsations. Also the time frame and there's not the fact that there's no presence of any other multi-wavelength components actually rules out the case of a changing at AGN. And in that case, they seem to observe certain spectral properties changing within time scales that are much more comparable to black hole X-ray binaries. But both the time scales and also the fact that this only happens in X-rays actually rule out that scenario. So all the things that I told you about and all the things that are now going to be in my thesis actually left me with much more question marks than answers that I was looking for. One of the things that this specific transient ULX introduced was, okay, we can say that given that the formation of the accretion disk is usually associated with an increase in X-ray luminosity, we can discuss there might be an accretion disk forming, and given the spectrum is actually very soft and no pulsed emission, assuming that it might be a neutron star, is actually very consistent with everything that we know, but it doesn't really explain why we actually destroy this accretion disk and never see it again. One of the things that were introduced specifically for neutron star ULXs is the propeller regime, where with changes in the luminosity or the mass accretion rate, the co-rotation radius of the disk can actually move within and outside of the magnetospheric radius. If you reach a certain point, your accretion disk will actually get destroyed and you will not see any emission. But it happens in a very fast way. When you look at the long-term evolution of these light curves, you will see, okay, there's some emission, but then there's nothing. Even if you have continuous observations, this will actually produce a bimodal distribution. In our case, you might call it a bimodal because there's nothing one time and there's something on the other, but this evolution is really usually expected to happen in observable timescales. It is not clear whether we can have such long propeller regimes. Some people might argue that if you have a lowly magnetized neutron star, this might happen, but it's also a very controversial discussion that I've had with some colleagues. There's another scenario which is called the MAD. I really like the name, but it stands for magnetically arrested slit. So it tells you that the more you accrete material, in contrast to the traditional solutions, it also accretes magnetic fields with it because it's an ionized gas. And the more this happens, the magnetic fields within that compact object, whether it's a neutron star or a black hole, will actually act as in a similar sense to the propeller regime, and your accretion disk will actually get dissolved, and you will be able to see a sudden stop. But this is usually expected to happen with the presence of or the launching of a relativistic jet, which in our case we did not really see. One of the other things that we might also need to consider is the viscous timescale, which will tell how stable your accretion disk can be within a different timescale. So this might change depending on the choice of your accretion disk model. In this case, we might actually start questioning, okay, what exactly is the model that we need to choose for ULXs? But that's a whole other conversation that I might need to work on maybe a few more decades. But in a more general sense, this specific source now contributes to a growing population of serendipitously observed transient ULXs. But in this case, they do not seem to actually have a very well-defined distribution in their long-term evolution. If you just exclude the propeller, the sources that are found to be in the propeller, the rest is a whole big mess. And now, but the problem with that is that we cannot really point any instrument towards any direction and say, okay, there has to be a ULX in this specific field of view. So what happens is that it was also in my case that when you're looking at something else and then you find it, or you can actually create algorithms that specifically search for it within the publicly available data sets. But that's also that will also depend on how you define certain parameters to actually describe the ULX. So it's also a bit of a mess. If it's hard to say that if we're on the way to actually get a unification of these transient sources, or we can just drop everything and open a bakery somewhere in the Alps. Hopefully that might be a good option. So to be able to summarize everything, my results so far showed that there's a very big significance in the proper modeling of the accretion disk, which needs to include the relativistic solutions, relativistic corrections to the photon paths around such compact objects. The black hole spin might be a determining factor on the evolution of the accretion disk temperature and the position of the inner disk radius, because it also defines the position of the innermost stable circular orbit. Now transient ULXs are kind of unique subpopulation of known binary systems emitting in X-rays. That's why I wanted to include the ULXs in X-ray binary population. They are either like very unique subpopulation we need to study, but maybe they might be also having the missing link that we need to explore if we want to unify the accretion phenomena across different compact object mass and also luminosity scale. And the existence or even the recovery of those deviations in the luminosity versus temperature relationships, maybe we can use that as a kind of an inferring the discussion for a black hole accretor, or there might be some sort of a missing link between that two cases. Maybe in the future I'm able to explore, and I will actually leave you with what I think is actually how you occur the space-time. And thank you for your attention.
And actually, the question to start and the comment there, for the connection between luminosity and temperature, did you fit the inclination of the system or did anything?
No, those parameters were very well constrained for these three cases, except for the black hole mass for GX39-4. But for that, I didn't go into analysis with CARBB just yet because it's not that easy to do it. But in the case of GRJ1655 and LM6, they are very well constrained and fixed.
Why for the vector spin, the diagram you showed with different spin depending on something. Doesn't surprise me very much in the sense that we know that there's a lot of uncertainties depending on the inclination of the system, but you are saying that you know this very well. Emissivity profiles, the position of the radii when you break the disk. So, I mean, of course, it's nice that you discover that even with the lot amount of spectroscopical data, we recover this kind of uncertainties that is telling us probably that we need something more.
Yeah, that is the thing that I'm trying to explore because there's also some discrepancies between the modeling of the relativistic reflection versus the modeling of the accretion disk spectrum. There's now a very nice model that actually has a very good continuum that also includes the relativistic reflection that I will be trying to do with GX39-4. So we will see how the results are going to be ending up, to say. I think there's anything to say.
Just maybe sometimes I ask this question. I don't know if you have the views about for U1630 of IXP. It's basically transient Radesh is
I know the transit.
In IXO state, that shows that the polarization increases with energy. And this is at odds with all the model of standard disk. I don't know if something can be said on this if you actually study this.
I personally did not study. My presence in projects related to XP is very recent.
Okay. Because then there is a lot of stuff.
Yeah, I also heard a discussion about, I might be mistaken if it's Sigma 6.3, that was later thought to be a galactic ULX, right? So I know that there has to be some sort of a dependency on specifically the accretion disk geometry and the thickness. And there might actually be some sort of, I don't know, changes in the polarization angle and degree depending on that. But I think I'm not really qualified to have any comments on it.
First of all, congratulations for the drawings.
Thank you. Thank you.
I was curious about the measurements that you showed on the 1655. Are they
Which
all
ones?
1655?
No, which measurements? Black hole?
The temperature versus
The luminosity?
yes.
Okay.
Which time scales are the observations? Have you seen the details of the light curves, like short bursts, or you just average over long time?
There are no specific bursts on a short scale as to be included in a one observation. But when you look at like this specific outburst is actually around maybe 120 days. So you do see increases in the luminosity, but not on the short time scales to be fitted in one observation, which is around maybe 10 kiloseconds. So in that case,
didn't go into the details of it.
I went into the details of these specific states. So I looked if there are any outbursts happening or anything variability that might account for something, but it was not that obvious or significant in this case.
Students.
Thank you for the talk. So my question is possible to like assume one of those models, okay, maybe there are still too much uncertainties, and then recover the scope to find out if like those are Kerr black hole or if there are black hole mimickers or something like that, or is still too much uncertainty around the model?
So for that, that's what actually people were trying to do very early in the mission of RxDE. But the problem with this specific instrument is that it only goes down to 3 kV. So you actually are missing a big chunk of this very teeny tiny emission here. If your accretion disk is much warmer, then yes, this tail will expand to visible ranges with RxDE. So you are only depending how well you can model that teeny tiny tail left in your observed spectrum. Which is very nice with RxDE. You can still do it to a very nice constraint, but it's not that well understood if this specific, for example, I will show it in the case of KYMBB, that even in the case of the closest that you get to the black hole, this actually does not go to ISCO. There is some uncertainty, as I said, due to the how do you say it, instrumental capabilities, but it will really depend on how well you can put your trust that it actually goes there. So it will be very difficult, but you can use that kind of an approach with relative action modeling, from which you can get a better train on position. I don't know if I'm missing anything, but this is mostly a better way to see if the emission is coming from. That might be more reliable if you want to do that. Okay.
I'm wondering if the deviation of the flux versus temperature could be due also, there could be a big bias, like different instruments, data instruments you use to construct.
Well, in this case, this is only RxDE. What I ended up doing was finding simultaneous either XMM Newton or integral observations, and then I repeated this via the spectrum.
And did you find with different instruments the same deviation?
If I only include integral, the deviation is still there. So unfortunately, I cannot recover it. But if I look at, for example, the lower end of the luminosity with XMM Newton, it was actually a very nice recovery to lower temperatures.
Yes, because I'm wondering if it's lower flux.
Yes, that was actually very simple.